What's up, guys? So many possibilities, and you decided to come here. A video on thermodynamic systems. Wow, respect. This level of craziness needs to be rewarded. Let's go! So, what exactly does the abbreviation DNA stand for? Nope, I don't care either. This is a video about thermodynamic systems, not abbreviations after all. So, thermodynamic systems. What's meant by that? It's really easy. If we want to look at any contraption, we first have to figure out where it starts and where it ends. Think about a car. Maybe we just want to study the engine thermodynamically, in which case we don't give a damn about the spilled milk in the trunk, nor do we care about any other part of the car. So let's draw the boundaries of the system around the engine. On paper, we draw a dashed line around the system that we're interested in. But what good does having a boundary system like this do for us? Well, first of all, it's easy to see exactly what you are investigating if you mark it clearly. This helps to avoid confusion and stops you from suddenly starting to involve surrounding elements. But the most important advantage of a system boundary is that it means we can enforce balances. And what do we want to balance? Just two things, actually: matter and energy. We want to know how much matter and energy comes into our system and how much goes out again. Luckily, a few bright minds have already given this matter a bit of consideration. Let's take a look at the types of systems we can have. We'll start with the worst kind of system, and that is the open system. Open in this case just means that both energy and matter in any form can enter the system. And of course, both can leave the system as well, like a heat exchanger, for example. Here, water flows through a tube, and obviously it comes out again at the other end. This water might be heated at one point, for example. If we take a look at our system, we can see that both matter and energy can cross the boundaries of the system. For our second example, we have the so-called closed system. The differences between this and an open system is that for a closed system, matter cannot cross the boundary of the system. Can't go in, can't come out. But watch out, energy can be brought into or taken out of the system just like before. Would you like an example? No problem. Think about a pressure cooker. If we close the lid, no matter can get in or out. But fortunately, we can still pump energy or heat into the system. Otherwise, a pressure cooker would be completely useless. So in this instance, the amount of matter in our system doesn't change, but energy is constantly being added. The calculations for this kind of system are a bit easier because we don't have to worry about how much matter is coming or going. And now for the last system, the isolated or self-contained system. Here, even less energy can get across the system boundary than in the closed system. And even then, there was only energy left crossing in the closed system, so that's all there is left to cut out. In an isolated system, nothing crosses the system boundary. Nada. Absolutely zilch. No energy allowed and no matter either. An example of this system would be an ideal thermos flask. Ideal because in real life, a thermos flask is not perfectly insulated. After 1 week of being in the flask, even hot tea turns cold again. But not so with our ideal thermos flask. If we fill it with hot tea and close the flask, we have an isolated system. No matter can get in or out, just as no energy can get in or out of the system. Unfortunately, such systems very rarely occur in tests because there's not much to expect from them. But at least you know about this type of system now. Okay, let's sum it all up. Thermodynamic systems are defined spatial regions. These systems then also have a system boundary that is in contact with its surroundings. We've also gone through the three main types of systems. There are open systems, where both matter and energy can enter and leave the system, then closed systems, which only let energy cross the system boundary, and isolated systems, where neither can cross the boundary. Nice! Now we've got an important foundation of thermodynamics in the bag. So you can go straight on to the next video.